Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Computer Wednesday, we're going to talk about Microsoft Majorana 1. So let's dive deep into it. Now this Majorana 1 is basically unveiled in February 2025 from Microsoft, and apparently it was built in Quantum Lab at Netherlands. So it is what it is. Now it's why is so much excitement about it. A, very good marketing. B, it's completely new architecture. Meaning right now there are more than 10 companies working at basically quantum computer, and all of them are more or less kind of agreeing this is how we're going to move forward. So this is a completely different pathway, like the toolkit is different. So I think in this way everybody is running on electrons. They are like, what if we run on photons? So fundamentally different things. And for the first time on paper, they can now see a pathway where you can have a million qubits processor. Meaning right now you cannot have error correction in quantum computer as easily as you would think, simply because in quantum computer you requires another superposition element to rectify it. So for that reason you have to have another quantum computer. So if you have basically elements, 8 qubits, you might as well need 8 qubits to error correct it. That's why we cannot scale it up. But again, Google is like really, that's why Google achievement few months ago was so big, because they finally cracked that limitation where they're like, no, we can increase it. Again, we do have to allocate some qubits for error correction, but it will not be like, you have 10 for computation and 10 for error correction. You will not have that issue. So this company is claiming that we are so good in terms of our resistance of error that we can in principle have a die like this and have million qubits into that. That's huge. That is huge. Flat out, let me be very clear. If you could actually do that, have 1 million qubits here and it actually works, the end, like flat out, that will be quantum supremacy. The end, like the end. So it would be very awesome. Now ISD, why they can do it and nobody else is even claiming that? Well, simple reason, comparatively noise resistant. Meaning once you go into quantum computer, what the hell that means? That simply means you are using a fundamental property of superposition. Basically you can be either on or off or both at the same time. Superposition. Now superposition requires you to be chill, like almost chill to be as close to absolute zero as possible. So your quantum computer works like that. And after that, problem is that that state is so unstable. Once you actually go into that superposition state, it's unstable. That entanglement is very unstable. It's so unstable that any random stray photon can just knock it out. Now you're like, why would there be random photons? Well, you live in Earth. Earth has something known as background radiation. So no matter how much shielding you will do, there will be some photons that will go through. And then we also have something known as cosmic ray. Now you only have few of them, and they are so sensitive that even one of them goes bam, bam, that's not acceptable. Now again, because our computers are so resistant, we can stable in terms of error, we can utilize error correcting code. Your RAM has that, high-end RAMs and server RAMs, and again, especially things that fly in the upper atmosphere and satellites, they have a lot of error correction to handle that. Quantum computer is so unstable that it's like it will barely last 1 millisecond, 2 milliseconds. So what they have achieved is a new structure that allows them to be chill. They're like, bro, we good. Now again, we are still talking in seconds or 2 seconds, but again, everybody is barely lasting milliseconds or microseconds, and you are like, yeah, we good for a few seconds or maybe even a minute. That's huge. That's why the fact that they are comparatively noise resistant is such a big deal. That's why so much hype is happening. Now, so we are talking about this topological conductor. What does that mean? That simply means topology. We are talking about the mathematical concept of a property, not the stuff itself. So it's not a name of something, it's a property, it's a basically a hole. Like there is a hole in a donut, there is a hole in a wall, whatever have you. So it's just a hole. Same thing here. Topology is a mathematical construct that describes something. Now, whenever you are going this deep into quantum physics, is just like that. So Eton Majorana predicted basically particle. This particle, Majorana particle, was predicted in 1937. Yes, ancient technology. Now, why this is such a unique thing? You have to understand there are more than a lot of state of matter, but stable state of matter we know. So basically, you know, solid, liquid, gas. If you're a little bit inclined, you studied general knowledge, you know there is a state above gas that we call plasma if you have high energy, and there is a state below solid if you have a very low temperature that we call Bose-Einstein condensate. But here's it. That's the 5 basic one. Then you can have lot of super duper hyper rare states, almost 20 of them. One of them is this puppy. So that positive and negative stays in a stable state. Now, what the hell does that mean? That simply means most particles, once you really dive deep into it, basically, if you dive into a human biology, what is the lowest level? Lowest level you can go to is cell. Once you go inside the cell, you are no longer at biology, you are at mechanical level. So that's why we say cell is the building block of life. What happens, building block of matter? It's atom. What happens if you go inside it? Well, you are no longer in the atom. Basically, if you go inside the atom of copper or inside the atom of gold, they're same. It's just the numbers are different, but the effect of that number, the property of that number will affect only once you have outside of atoms, not inside it. Basically, inside is like, I'm going to take this electron. This electron does not care whether it's in uranium, copper, or gold, or whatever have you. I'm going to take this nucleus. It does not care. So for that reason, you have to understand, matter has a layer known as atoms. You cannot go inside it. The properties will change. You go inside that, it's like, okay, let me understand what the hell is. You enter the realm of quantum physics. What happens inside this? Who knows? Like, that's the best answer I can give you. Who knows? Like, it's a freaking weird magic layer where things happen. Things happen. Things can be multiple places at the same time. And then generally, if you go really deep into it, things are like, there are stuff, pujung happens, there's like positive particle, negative particle, they collapse, go poof. Like virtual particles that are being created, 0-point energy or something like that. It was like being created and collapsed. And yes, somehow we have mathematicians who are that good, they can understand that. And he is one of them. And he figured it out. If we have, and all things are like this, matter and antimatter. So if you combine them, go poof, positive and negative, combine them, poof. And somehow he figured it out. What if there was again, mathematics is saying that you had positive and negative, they can coexist mathematically. So that's the whole point. And this is what Microsoft has achieved. That's why they are saying new state of matter. We have known this. It's just that nobody has achieved it. Now, people did try to find these particles in Large Hadron Collider and things of that nature, but that was high energy. Basically, we wanted to go boom with a super duper high energy level to find particles. We did, but not this sort of one. So there is a different realm. So high energy particle, that's one realm. Freeze that puppy, that's different. So this property of quantum state is what is being utilized for quantum computation itself. It's not like, okay, I'm freezing an atom or doing computation on a photon level. It's this topology that is doing the nanowire itself. Now, fundamentally, it's not limited to an atom. It could even be happen to 100 atoms or 1000 atoms, or a wire that could be few microns. So, or nanometer basically. And why the heck it's such a big deal? Well, here's the deal. The fact that it has positive and negative gave the idea, what if we stretch them, positive and negative, and we put them on both ends. So you have positive on one end, negative on another end, and they are in now superposition, meaning you can do the computation. But here's the deal. The stray photon that is like, bane of everyone's existence, if it goes through one side, it does not disturb the system. Why? Well, negative was intact. It's literally like how we do differential signaling in all our electronics. For example, if you have seen microphones, they have 3 pins. Even on a single mono microphone, they have 3 wires. Why? Well, one is ground, another is differential. So positive and negative, they are in differential. And your basically receiver on the other end compensates for it. Now, benefit of that is all the noise that happens in the wire gets cancelled out. And again, that is same concept used in your Ethernet wire, HDMI wire, everything almost. Digital signaling relies on that. So somebody figured like, what if we have positive and negative, meaning even if it gets interacted by one particle, it does not care, the second one is intact. So that's why it's so resistant compared to every other system. Every other system, you are compensating for it. This puppy is like, I got this. I am actually stable on my own. And that's why they wanted the wire to be thick and far apart, where you have the probability of photon interaction happening from one end, not affecting the other superposition. So, but let that be very clear, this is my best interpretation of this magic level technology that we are talking about. So flat out, the fundamental base is so stable that they can scale it up. And this etching process, that's anything like normal etching. Like if you call up NVIDIA and TSMC, they're like, yeah, we can make 1 billion in one. That's not difficult. If you can sustain the quantum state and it's stable enough, everything else becomes okay. So this is the whole point. This is why Microsoft has been working for a long time into this. Now you have to understand, fundamentally the path is long, like ludicrously long. Now math has been known, like Richard Feynman figured this part out long ago, where it's like, okay, we cannot predict our real world reliably because again, we are just crunching on the computer front. That's cool and all. The moment you input long complex compound chains, yeah, it breaks down. And that's why we are using AI to guess how the protein folding happens. We do not know how to simulate it. We are not accurate enough. We cannot make a medicine and know for a fact that it's gonna. We can guess it, we can try it, and again, we have been doing that so far, but we do not just like, this is a compound, computer, simulate what the hell is gonna happen. It's like, yeah, I do not know. I do not know. Not no AI and all that. AI can guesstimate it, but again, inherently you want the ability to actually compute it. If you have few molecules, few atoms working in one molecule, computers are powerful enough where they can crunch it. But if you add like 20, 30, 50 molecules, atoms in a molecule, computer is like, bro, I'm out. If I have to truly simulate it, I'll be here forever, like literally for as long as the universe is. So fundamentally, you need quantum elements itself doing the computation. Without it, you cannot crunch it. So we know the mathematics, we know why we need it, all those things are sorted, and people have been trying everything under the sink. For example, photonics qubit, where you are using photons, trapped ions, and there are 10, 20 more of them. So trust me, there are a lot of it. And right now the key is to make a qubit that is quality qubit, meaning they are stable enough where you can actually compute it. Not just like for 5 femtosecond we achieved qubit. No. You need it to be long enough where you can run calculations through it. So that's the difficult part. Now, all of them, all the metrology and topology, all of them have some pros, some cons, and some limitation. That's the reality of it. That's why so many of them are here. We have not reached the pinnacle model yet. Now, Microsoft have been at it for freaking 20 years. Yeah, this is a long, I'm getting old, 20 years. And their station queue was established just to solve this in 2006. So yeah. So Majorana one chip is 8 qubits right now. That's it. Done. Go home. 8. So now let's compare it to Google, which again announced very quickly. Now Google is more of a quote unquote traditional, but again calling quantum computer traditional feels stupid, but it is what it is. And they have made significant progress. Flat out, if you stop the stopwatch of progress right now, Google is ahead. And they have 105 qubits. Now again, that is their whole point. Everybody knows how to make quantum computer. Every college, university can do that. It's just that nobody had figured out how the hell you scale it up with before error destroys your everything. They have figured out how to do error correction or error resistant compute, where they can compute it, basically make it, run it for a few milliseconds, and that is more than enough for quantum computer to actually crunch the number. And that's why they came up with the idea. We ran this calculation and it actually gave us the answer. It lasted long enough. So they did that, and they have 105 qubits. So that is significant. That is not like lol. That is significant. So they have made tremendous progress. Not only they have something that actually works and does the computation. So that is fundamental. And again, their core competency is error correction. They figured out how to handle the error correction part of it. So on paper, they are also viable and they can scale it up. And given the fact they are slowly scaling it up, they had 15, 25, 40, 100. So they have been scaling it up. So they have pathway and they have history of the milestones that they can actually do it. So as of now, in March 2025, flat out, they can do it and others are claiming to do it. So this is a very big achievement from Google's point of view. So that's there. Now, what can we expect in the future? Well, let that be very clear. The marketing was bit too much, like a lot, kind of stupidly lot. And I am fed up, like almost like somebody in marketing figured out a cool word and they're like, everybody must memorize it. And they keep saying this and they've been doing it for the last 9 months. It's like, the path to million qubits. It's like, that's path to infinite energy. That we have fusion, path to infinite energy. We don't have it. It's like path to anything means nothing. And be mindful, right now the world record of qubits is 5,000. And yes, different type of qubits, but qubits nonetheless. Superposition nonetheless. So fundamentally, even if you had double digit, like at least 11 qubits, I would like, okay, double digit. Like Google has 3 digit, 10, ones, tens, and 100. They can say 100. Now they have enough zero so that I can see them in the graph. I cannot see you in the graph, my man. Million, saying that million. And if it was that easy, at least, come on, at least have 10. Or again, practically, you should have waited long enough where you can have 200. But like, why the heck you not? And you've like, path to million is unlocked. Okay, how about path to 200? How about just do that, just out of spite? It's like just, oh, we have reached 200 qubits. Like just out of spite. They couldn't. That's how I know. And one of the very senior person, like very technically educated and all that, is saying, and I'm pretty sure either marketing taught him or he believed him in his whole self. Whereas like, oh, engineer, the science is solved. It's just the engineering problem now. I'm like, science of this puppy has been solved for I don't even know before I was born. Ancient technology. That puppy is ancient technology, before black and white movie kind of technology. So like we know what that was. We just don't have the actual engineering of it, like physics, engineering, economics, let alone economics. You haven't even crossed the engineering problem. It's like, oh, it's gonna be like 8 years and all. I'm like, bro, 80 years that has been going on. So what? So that really like again, you have 8. If you're 80, 200, again, 200 would have been a sweet spot, and like, rubbing salt on Google's wound. But this 8 is like, no. So, flat out. And one thing you have to understand, this will not solve our problem. It's just a tool. If tool is utilized by users wisely, awesome things will happen. If not, nothing. It's like you can have AI, and somebody can use that AI to actually do something productive or something, just make fake porn out of it. So, do not think that this tool will solve things. It's up to the person utilizing it. I'm seeing way too much of that, like this tool will solve global warming. It's like we had solved global warming. We just don't want to actually fix it. It's a human psychology problem, not a technology problem. And this tech bro mindset is like a really frustrating thing for, well, anybody who understands science. It's like, bro, we have the solution. Rudolf Diesel solved the problem before it was a problem. So it's one of those things where it's like, this tech bro, like only if we had quantum computer, all our problem will be solved. No, it won't. It won't. So it's one of those things. That's why I want you guys to come down to earth and be very mindful whenever, oh, it's just an engineering problem. Just an engineering problem. Everything is a goddamn engineering problem. Oh, this is awesome stuff like triple junction solar cells. It's a normal thing. We buy it, we use it in satellites. It has up to 51% thermodynamic efficiency, and we just don't use it in our terrestrial solars. Why? It's expensive. It's just an engineering problem. So it's one of those things where it's like just engineering, but that's the whole problem. So again, 8 years is, I'm like, bro, again, once they start to reach 500, 1000, 5000, now we are talking. Right now, they are too early. They are celebrating too early or creating marketing too early. So this was my presentation on Microsoft Majorana 1. Hopefully you have liked it, learn from it. In that case, please click the like button, share it amongst a friend. That will help me out. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.